during this meeting. I would like to report about a program which started 2 or 3 years ago on the numerics of the S stands for stochastic, LLG stands for ferromagnetic PDE, and it was 2 years back when I gave a first talk here at this place on first results on this program. I would like to continue, and I apologize that some results will be also will come back from this earlier talk here as well. I will continue with reporting on the results which we obtained in particular over the last 2 years. So this is a joint work with Lubomir Banash from Edinburgh, Czesław Brzeziak, and Misha Neklyodov. So the equation that we will see in a minute, the LLG, the Landau-Lifshitz-Gilbert equation, is a constraint for unit vector field. So we are chasing for mappings which go to the sphere. And in particular, after the first part, where I talk about numerical tools to approximate these solutions of Landau-Lifshitz-Gilbert equations, in the second part, I will talk about the stochasticity, which is involved into the stochastic LLG equation. So as I mentioned already, as a numerical analyst, I would like to understand, or I would like to construct convergent discretizations for the Landau-Lifshitz-Gilbert equation. So I'm not chasing for rates of convergence in some sense here, but I'm trying to construct a practical method to construct weak solutions. That's all. So what I'm interested here, and which difficulties need to be addressed will be reported on in the first part of my talk. So then I'm already armed with some numerical tools to approximate the solutions of the Landau-Lifshitz-Gilbert equation. And then I can step over to part 2, which will be on the stochastic Landau-Lifshitz-Gilbert equation. This model actually was created, I can say, by Brown in the early 60s to describe single spins, single ferromagnetic spins in a heat bath. And a generalization which leads to these SPDEs will be discussed in part number 2. And the part number 3 is essentially new here, and I will report on n-particle systems. So I'm switching to from the, let's say, more complicated case to the more easy case of SPDEs in order to understand better long-time behaviors, both with respect to analytical results in the context of finite dimensions and corresponding numerics. So this is the construction of martingale-based martingale solutions for finite times. For SPDEs, this is the long-time asymptotic study for SPDEs, SODEs related to this problem. I jump over this slide, which is a photography of a ferromagnetic device, and where we see so-called Weisschen domains, depending on what color what we are seeing here. So white colors means that we have local magnetizations which say look from top to bottom, and not white but black areas from left to right. And in between there seems to be some sharp interface. And this is an interesting phenomena, these Weisschen domains and corresponding walls in ferromagnetic samples. So I give here a sketch for the same phenomenon of energetically preferred ferromagnetic states. I think I made a mistake here with these 2 arrows. Depending on geometry, which means we have here platelets, think about dozens of nanometers size, and depending how tall these platelets are, there are different ferromagnetic patterns preferred depending on the geometry. So physicists talk about Landau state, I think this is called diamond shaped state, etc. So there's a coupling of energetically preferred, I did not specify the energy so far, but of energetically preferred magnetization patterns and geometry. Another thing is that if we zoom into this transition here of neighboring Weisschen domains, we see actually that there is a diffuse transition. So on a different scale, we observe what for physicists is well known as Bloch walls or Néel walls or even more complicated structures. So it seems, with respect to space, there are lots of phenomena occurring on different scales. But it's not only space, but also time effects. And I think this picture here in particular will be very important to understand the LLG, the Landau-Lifshitz-Gilbert equation, which will pop up on the next slide. So what we see here is a magnetization arrow, or it's here, of length 1. And this guy, sitting somewhere in our ferromagnetic specimen, performs a precessional motion around an exterior, around an effective field, H effective. So we have precessional motion to occur, some conservative phenomena to occur. But this is combined with some dissipative effect, which is a damping, which is phenomenologically observed. So what happens is that this is rotating and rotating and rotating, but it's approaching the direction H effective at some point. So these two effects, conservative and dissipative, make it very interesting, as we will also see with respect to stochastic effects later on, and for instance, to study long-time dynamics. So driven, for instance, from applications in hard disk storage industries, where things become smaller and smaller, you can think about a model which involves temperature effects, thermal effects. And this is actually the idea of Brown, the guy that I already mentioned, who in the early 90s discussed, brought up the study of single spins. And if we are thinking about infinite ensemble of spins, which leads then to the S LLG. So to summarize my motivation, we have different multi-scale effects in space, time, and eventually also stochasticity. So let me start with the first part, the deterministic Landau-Lifshitz-Gilbert equation, and let me highlight problems for me as a numerical person which needs to be overcome to construct, to practically, my emphasis is on practically, to practically construct corresponding weak solutions. See, there is always a possibility to use abstract Galerkin methods to construct corresponding solution objects, but I cannot implement by using these tools corresponding approximations. So this slide somehow summarizes the Landau-Lifshitz-Gilbert equation. So before I turn into more details, so this is again the precessional part, which I gave a picture about just a minute ago. And with a small parameter alpha, the term, this guy, in a minute we will see it's cubic with respect to m. This guy is making the dissipative, realizing the dissipative effects. So let us recall the situation. The guy is standing here, and then there is the effective field acting onto him. So the effective field comes from an energy, and the physicist tells us what energies are acting through this effective field on the magnetization M. So there are lots of effects, and I only will talk about this exchange energy. So if I make the derivative of this energy, we will get a Laplacian in a minute. But there are also there are other effects also imposed to this, contributing to this overall energy. Physicists talk about anisotropy energy, exterior energy due to an applied exterior field, and maybe some more non-local effects. So if I now enter this effective field to my equation, The overall equation, I just repeat it, is the following. Mt is equal to, I hope I made the signs correct, is equal to this guy minus alpha m cross Laplace m. So this is the equation, and there are now some very important properties which I will use to construct then corresponding weak solutions. So the first thing is that the change in length is 0. So once we are starting with a unit vector field at the beginning, so the unit length property will not be violated for positive times. How does this happen? So by classical calculus, I hit this equation by m. So m times mt leads essentially up to a factor of a half to the left-hand side here. So m squared and the time change in front. And the guys on the right-hand side will be gone then, because it's the basic formula a cross b times a is 0. So we have this conservation of length pointwise if we consider it in this motivating discussion. So another thing is the energy identity. And I was now mentioning already that I only would like to stick to the leading part, the so-called exchange energy. So if I'm now not multiplying by m, but if I'm now testing by Laplace m, and I'm emphasizing the fact that I'm here testing by Laplace m, because in a minute we will see when I use finite element functions, Laplace m does not make sense. So if I'm multiplying by, I'm testing by Laplace m, so then we get an energy identity where we again see dissipative effects and the evolution of energies. So these two properties can be exploited to construct. So I'm here in 3 dimensions, for instance, to construct weak solutions, non-unique. And this has first been done by, as far as I know, François Salouche and Sauer in '92. So let me come back to the very first interpretation of this problem. So it's a ferromagnetic equation where we have precessional motion together with dissipative effects. And if we now only consider in the given framework the guy which is led by alpha and delete precessional motion, then what we arrive to is heat flow harmonic maps to the sphere. So we already know from, for instance, results by Struve and Yunmai Shen in the late 80s in 2-dimensional setup already, so this has to be properly then defined, that we have to expect finite time, finite energy singularities. So now this is, we have this additional precessional motor in addition, and perhaps we are not expecting better solutions than those which occur for heat flow harmonic maps, meaning finite time, finite energy, singular behaviors. In order to motivate what I'm talking about, I will show on the next slide some simulations which evidence also for this situation singular behaviors. In section 2, it will maybe be interesting at that point what will be the effect of noise in the context of singularities. Yeah, U stands for the magnetic gradient. U stands for the magnetic potential. I don't want to talk about it. So here are some pictures. Unfortunately, we don't see this maybe too well. We are starting. This is a top-down view of an initial vector field, which is essentially the one that Struve used for the heat flow harmonic map scenario. So now what we see here is the situation of a bunch of flowers. Think about a bunch of flowers, and they make a rotation by 180 degrees from the original one in a symmetric fashion to those guys looking downwards a little closer to the boundary. So this is the initial profile that we have here. So then this is combined with a precessional motion, so which we have for the Landau-Lifshitz-Gilbert equation. At positive times, what we observe is a situation that is close to blow up, where essentially one guy is only looking upwards, so he does not know, he is not so much affected by the precessional part and also not by the dissipative one, and the other guys are looking downwards. So this is the situation close to a blow up, and for this reason we have a motivation. Unfortunately, there's no analysis available so far for the Landau-Lifshitz-Gilbert equation, which shows or which proves singular behaviors, possible singular behaviors of solutions. But this is a motivation, a numerical motivation that the problem is not so easy. So as I started with in the beginning of my talk, the goal for me as a numerical person is to construct convergent discretizations without hoping for any rates or for any regularities. Okay, what are my constraints as a person working with finite element functions? Finite element functions or the finite element method is a special Galerkin method. That's the most important thing. And the second thing is it consists of piecewise polynomial functions. Right? Where we are piecewise polynomial, so there will be a problem how to all the time meet the sphere constraint. So I mentioned this already. This is a crucial issue here for the Landau-Lifshitz-Gilbert equation. Another thing is that globally we are dealing with objects, finite element functions, which are not smooth. So what does it mean to apply the Laplace to such a finite element function? And this was needed to get an energy law. So another thing is, what about time discretization? We certainly don't want to use time damping schemes. So since we want to keep the sphere condition in some special sense. And the sense will be as follows. So the constraint will be relaxed to those points which are particular points, which are nodes of my mesh. So let me detail a little bit, since I'm not expecting that anybody is familiar with finite element methods, some small results about general principles, I mean, about finite element method. So we have here a domain O, this is our ferromagnet, and we make a triangulation to cover, etc., to cover this domain. So the triangulation, which is parameterized by my mesh size h, which I want to tend to 0 at some point, is consisting of, in this case, triangles or tetrahedrons in one dimension higher. So then we are talking about finite element functions. So and these are objects. In our case, they are R3 valued. With a property that phi, I should make a vector here for a moment, at each triangle K is a polynomial, in our case, of degree 1. We are using very heavily for the convergence properties of corresponding schemes that we are dealing with polynomials locally of degree, with functions which are locally polynomials of degree 1. So okay, so before I continue with some further ingredients which we need in a minute, let me proceed. So these are the objects that I'm constrained to. And now I would like to propose 4 solution strategies, meaning I would like to propose 4 discretizations, both in space and time, which all are able to construct weak solutions. by using my constraint tools, finite elements. So one strategy was proposed by Allouche and Jason back in 2006, where they propose to use an time explicit scheme where starting from a unit vector field, un, along corresponding tangent spaces, a new increment v of x, and tau stands for delta t, stands for time increment, is constructed. And this object has this length here. Obviously, it does not satisfy the length condition anymore, so it needs to be projected back onto the sphere. So then the step is completed to get a un plus 1 at a certain fixed place x as the successor of un. So this explicit in time strategy is can be analyzed in the context that the k, which is the delta t, is sufficiently small. So if you actually are running computations and you have a constraint like that delta t is like delta x to the 2.5, this is a very restrictive numerical scheme. So think about you have a ferromagnet and you have a mesh size 1/100. So then you can easily compute how small time steps you need to do in order to overcome an order 1 time horizon. So we get a perturbed energy identity in this context, and can then conclude that the scheme, which I did not detail, only the idea, we can conclude that this converges to an object which, surprise, surprise, is a weak solution. Okay. Another strategy out of the 4 that I would like to discuss here is Ginzburg-Landau penalization. So we are weakening the sphere condition by adding a penalization. This looks very nice, and is because we are free from sitting on S2 to the on S2, but this can lead to the fact that in particular, close to blow-ups, we cannot balance numerical parameters, time, space, with epsilon properly to mimic the blow-up behaviors properly. So I would say this is not such a good strategy, because we can only prove here that for first tending numerical parameters to 0 and then epsilon to 0, we construct we construct a weak solution. No link between penalization and numerics. The scheme which I would like to discuss here and that I will use in a moment for SLLG is this one here, and I would like to provide some more details because for the things which are sitting here. So the dt mj plus 1 is equal to 1 over k mj plus 1 minus mj. So this is the scaled difference quotient. So the mj plus a half, this reminds very much of the midpoint rule. I will see this in a minute. Is the combination, additive combination of those guys. Okay, let us talk about. Let us not talk about the role of numerical quadrature or mass lumping, how this is called in numerics, and the role of the discrete Laplacian, which we have here, which replaces the role of the Laplacian in the continuum context. But let us maybe think about this formulation just with respect to time discretization effects. So what we see here is that in order to have conservation of length over times, we are sitting at a special point x now. We are using as test function. This is not such a good idea, but we I mean more. We are multiplying by m j plus a half at a special place x. When we are doing this one, then we have a scenario like a minus b times a plus b. So this means a squared minus b squared. And these guys sitting on the right-hand side will all be 0. And this is the reason why we are constructing the scheme like that. So we are spreading information in time and space, basically. And we are using clever numerical integration, I would say, to get the properties which are needed, which is one, to have the sphere condition at nodal points, and second, a discrete energy law. The third strategy can be based on discrete Lagrange multiplier. I don't want to talk about this here because it's maybe too technical. So let me summarize. So the reason for the last 10 minutes was to motivate you that to construct the finite element time discretization is not so easy because we want to get the sphere condition and because we want to get an energy law. These were this in a fully discrete world. Why do we want to do this? Because eventually we want to use the computer for simulations, which I'll show you a little later. And the constraint here is the fact that we don't have regularity whatsoever that we can base numerical analysis on. So we can construct by such Galerkin methods, which I just proposed in the previous slides, weak solutions of LLG, and this is the best which we can do in order to study this problem, seems to me. Okay, so yeah, okay. Let me start. Correct. I think this is the best picture here. So we are all the time on this. This is one time level.
And then you have a linear interpolation.
And then I have a linear interpolation, and I see this here suggests that at all places, apart from nodal points, I don't have the sphere condition.
Yeah. But in the limit, then you have it.
In the limit, we can get it by using the fact that the finite element functions are boring functions.
Can you also prove analytically that the limiting equation then is on the sphere?
Yes. Yeah. So this is the limiting object is a weak solution of LLG with all properties that you might think of.
Okay.
Okay. Let me now turn to SLLG. So I already mentioned that Brown has come up with this formulation. I changed now the letter M, which stands for magnetization, to S, which stands for spin. And my understanding is that we are now moving from 10 to the minus 6 maybe to 10 to the minus 9 in meters. And we are now accounting for temperature effects. And magnetizations, M, are statistical averages of S. So that's the idea. So we have the same structure of the problem. And we have now a fluctuating field here. And according to Brown, for instance, it should meet the following requirements. So the expectation vanishes, and the correlation is like that. So we have no correlation in time. This is good. But also no correlation in space. That is what he wants. Okay, so I forgot to mention that the interpretation of the multiplicative noise in the corresponding problem, why multiplicative? Because here is an S sitting, and if we replace the red piece here by this red piece here, we see a multiplicative noise. So this has to be understood in Stratonovich sense in order to meet the geometric constraint, which is the sphere condition. So if we replace this Stratonovich formulation by Ito, for instance, we cannot keep the sphere condition. We have a drift part, which is the operator that we already know, and now we have this additional piece. Again, the goal is now to construct corresponding martingale solutions, 3D all the time, by using, let's say, practical Galerkin discretizations, which are finite element based. So I would like to use all the tools which I just showed to you. Okay, so we are using Neumann boundary conditions here, and at this place, for the, let's say, for the theory and for a better understanding of the numerics, we use trace class operator. I'm sorry, we use the Wiener process where the covariance operator is trace class. But I will give a further comment on this restriction later on by, in particular, computation examples. So, okay, in this context, we are hunting for an object which we, of course, all know here. So, we ask for a probability space, a Wiener process, and we want that this property holds in the limit for the limiting object, and this here is just the analytically weak formulation of the problem. This looks a little horrible because phi here is a test function which goes to R3, so please apologize that this means component-wise derivatives. So there is a result by Brzeziak, Goldis, and Jagurai, which are constructing martingale solutions to SLLG. So you might think problem solved, let's go to the next. No, I would like to have a practical discretization of the problem to make numerical studies for this. Okay. So the scheme that we are using, so you might think of an approximating scheme, is based on finite elements, and I'm using all the knowledge which I communicated before in a deterministic case, together with proper addressing of now the stochastic effects. So this here looks maybe familiar. In before I just wrote dt mj plus 1. Now I wrote this explicitly. Also this guy was already discussed as method number 3 in the catalog of for methods to construct weak martingales, weak solutions of LLG. And the only thing is now that we need to shift this a little back. So I'm sorry. So this is not delta h of sj plus a half, and at these places, like in the LLG scheme, related scheme for the new purposes here related to stochasticity. So we are discretizing in space by finite elements, in time by using, let's say, this trapezoidal rule, and also with respect to stochasticity, so by making simpler Gauss variables by replacing them by discrete random variables L2 valued. So the question Q1 is solved. The finite elements, sphere condition, and energy identity, does it hold for the discretization? So we talked about this quite a time, so we can use these concepts to achieve the goal. We have approximates which satisfy the sphere condition at the nodal points. Yeah? So it's very important to have this boundedness, you can imagine, for making the convergence analysis. So and also we have the energy identity, which tells us something about, in particular, the spatial variations for corresponding sequences of finite element functions. Also, we are making the Wiener process increments easier by approximating them by random walks. This is very often used in numerics at this place, and can use this tool to pass to limits, corresponding limits. So I would say, to summarize, the construction is again by an implementable discretization. This is a nonlinear algebraic problem. That's it. And we can construct martingale solutions by these practical approximations. We are using, I give a very brief sketch of a corresponding proof in a minute. We are using variational concepts, evidently, which are not so well known or maybe widespread in the numerical stochastic analysis at this phase. So an issue here is, since we are facing space-time discretization, how to construct discrete filtrations for every delta t and h, which is delta x, positive to construct limiting objects and identify limits for the stochastic integral. So the main result of this presentation here is the following. We can build from solutions of this problem, adapted processes, sequences of adapted processes, which converge to a martingale solution of the problem. So that's.
In this case, you interpolate the nodal point. You stay on the sphere with an interpolation, or you
again not. It's the same thing like before.
So the approximating process lives somehow somewhere else, not on the manifold.
Correct. So it's an exterior approximation. So the sketch of
possible just to take a geodetics or something like this on the sphere, to live on the sphere.
The point is you are restricted by the non-flexible finite element functions. They are just allowed to be polynomial. So we have the discrete sphere property, as just discussed at the nodal points. Then the second thing is we get a discrete energy bound, which controls, for instance, uniformly with respect to kh variations in space. So, but we also need to control variations in time to run then a compactness argument. And I'm sorry. So this has to be accomplished here. So then we can use standard results for, this is time, for piecewise affine combinations, non-adapted, made out of the iterates. In a minute we will see something else made out of the same iterates. So we are using piecewise affine constructions to then make a compactness argument, to use standard tools then and construct convergent sequences. And this is enough to pass to the limit with respect to the deterministic part. So now we have to, of course, deal with a stochastic integral, and this requires us to talk about adapted processes and corresponding filtrations. This is something which we need to accomplish then. And also we have to address the approximation of the Wiener process increments to then pass to the limit and obtain as limiting object for the diffusion the stochastic integral that we expect. So I need to mention that this is maybe a little bit naive. This picture is related to making the limit for drift. This is making the limit for diffusion. So these two objects are pretty close to each other, and this completes then the proof. So here are some experiments now. Since we have a numerical scheme, which is potentially able, I admit, by picking some subsequences, etc., on some filter probability spaces, which we don't have beforehand. So we can now use this numerical scheme to make some simulations. So the first is with colored noise. This is covered, and I will detail this in a minute with a numerical scheme by the numerical analysis, which we just discussed. And here we are entering a new area, so which is white noise. We have no control what our numerical scheme is doing right here. So here we made 2D simulations, and I just focused then, after the computation has completed, on single trajectories at the origin. So we see that there are two trajectories, so at some point there is an almost instantaneous switching process occurring. And so what this goes together with corresponding plots of the gradient of S in L infinity norm and the corresponding time evolution. So gradient S in L infinity norm, and we plot the time evolution. So we these three colored in three different colors, these three trajectories here motivate, not more, this is only computation experiments now, motivates that we have finite time blow-up behavior still with respect to trajectories. Another situation, but a little bit vague at this place, is that if we draw a corresponding expectation, it gets a little smoother. So we don't know, and now I have to be very precise. Here we are using R-valued noise, not more, R-valued noise. So we see that the expectations are clearly a little smoother, but we don't know if, since we are also, if we draw corresponding curves of energies, and the energy drops here quite strongly. We don't know exactly if R-valued noise is sufficient to give smooth picture for expectations. So now we use white noise, and I'm maybe overestimating this result, but I would say in the case of white noise, which is not covered by theory, we observe that expectations are smooth. And let me indicate, this is only an computational motivated statement. Let me motivate this. So first of all, white noise means for me the following. So we have a finite element grid again, and at every single point we start with an independent Wiener process. This is what we are doing. And then we are refining, and again we are starting again at every point which is nodal with an independent Wiener process. So you can imagine that corresponding energies lie on different levels here. This is a linear scaling. So the energies for the coarsest mesh is this red color, and I plot here one trajectory. So this zigzag type curve, and then I'm refining this by cutting h to h half. I'm plotting a corresponding trajectory, and again, I'm sorry, for the gradient of m, a gradient of s in L infinity norm. For the gradient of s in L infinity norm. So the height has doubled, which is maybe expected because we are able to better represent steep gradients. And there's even a big peak if we go from h to the 4 with respect to the gradient of m or gradient of s in L infinity norm plotted in its evolution. So the black curve here shows a very big, so essentially doubled with respect to blue, peak, which marks lower behavior. So now we plot corresponding expectations. And here the curve is not, it's also this quite smooth curve, looks quite smooth, but in particular, and then I plot the green and then the blue one, looks quite smooth. There is no multiplication with respect to peaks, which could indicate numerically, it's only numerical evidence, possible singular behaviors. So this page is to communicate basically that if we use rich enough noise, and I told you what I mean by white noise here, that we can hope for better results for expectations. So here's another plot, evolution in time, and the color encodes values of the expectation of S in modulus. So blue here stands for almost 0. Green stands for 0.5, and red, so the starting situation, stands for 1. So what we observe here is again, to my opinion, this looks pretty smooth evolution of expectations. We did also some studies pathwise, but I don't want to talk about that so far. So to summarize, the results of the second section are as follows. We have for trace class noise a practical construction of martingale solutions, and we were using this numerical scheme to then use more complicated noise. So let us now change a little bit the picture in the following sense. So let us now step over to the case of only n spins. So we have an SODE, only n spins. And this can be considered or also reinterpreted as an only Galerkin discretization, an only finite element discretization of the SLLG. And now we are asking what happens for t tending to infinity. So far we were constructing martingale solutions for finite times, and now we are interested in a long time dynamics for a much simpler, it's SODE system. So the equations look the same. So the effective field is put right here. So of course the effective field has to be adapted to the discrete world now. So the J is not the Laplacian anymore, but it's maybe a space approximation of the Laplacian. So the J is making this exchange term. The exchange energy term can be considered as a discrete Laplacian. So we ask what happens for time t tending to infinity. What can we say about limiting objects? And for me as a numerical analyst, most importantly, what can we say about the discretization we just saw on the previous slides with respect to the answers in 1 and 2? So let us start with a very easy situation, which is basically the Bi stands for the ith spins out of n, capital N spins. And the Hj is a fixed vector there, and we are putting R-valued noise to that. So it's maybe not too much surprising that we see that corresponding trajectories and with respect to distributions, this supports the picture that we have no irreducibility because there are big areas which are simply not visited. So the noise is, this low dimensional noise is not rich enough for a long time picture. And in particular, also, we get a Dirac here basically at the end. So this is definitely not a Gibbs structure, something which is needed to be compatible with statistical mechanics. So let's do a little more. Let's do high dimensional noise. And the Wiener, take an R3n valued Wiener process now. So at each spin out of the capital N many spins, we have an independent R3 valued Wiener process. And this picture looks completely different. So basically the whole sphere is covered by single trajectories, which motivates irreducibility. And even we can look closer at these computations to give a motivation that these results are Gibbs. So I have no time, but I would like to summarize the results of the last 2 pages here very shortly, which are addressing long-time behaviors. So the first is, let's take the good noise, let's say, the high-dimensional noise. So, and we are once more in talking about an n-spin system. So what we can see then is that we have the existence and uniqueness of an invariant measure, which can be, which is exponentially ergodic. So that's the result here. We cannot make explicit the related rate due to the tools which we are using right here. And more importantly, maybe if it comes to the role of noise, we can only show for Ci constant that the invariant measure is Gibbs. So this again gives the motivation that maybe, maybe not, that white noise is a good candidate, not only to deal with blow-up behaviors, but also with respect to physically compatible long-time dynamics. So the last slide simply says the scheme which we have discussed in an infinite dimensional case with respect to time discretization phenomena is also creating a unique invariant measure, need not be Gibbsian anymore, but it converges to the Gibbs measure that we obtained on the previous slide. Thank you very much for your attention.
Thank you. Any question? Please.
Maybe one question on the behavior with respect to alpha. Can you say something about the error and the convergence of your schemes and so on with respect to this dissipativity parameter alpha? How does it matter what alpha I put for your numerical schemes?
For the SPDE scenario.
For example, yeah.
So for the SPDE scenario in particular, this is the dissipative term, and the whole analysis lives and dies with this piece. So alpha has to be positive. In applications, it's very, very small. So another thing is there are physical principles which require alpha to be positive. So there is fluctuation, dissipation theorems, so which force you to be positive with alpha. But if you do not do that in experiments, we can also not get Gibbs structure, if I remember correctly. Did I answer?
Yeah, I was rather thinking about an error term for the numerics, and if I make alpha smaller and smaller, maybe that error term blows up or something like that.
So of course the limiting, so this phenomenological term is very important, and maybe you are interested really at the case alpha equals to 0 and then to study the interplay with noise mathematically. But I'm not sure what it means physically.
Please.
Yeah, I'm just wondering, I mean, if you do numerically or whatever, if you check what your schemes do with respect to the energy function. And you are pumping, I mean, the noise is pumping energy into the system, right? Whatever you do. So what is the observation? Did you check that? I mean, like the second, the energy meaning the Dirichlet energy of your...
Yeah, so we see that here's a plot for the energies.
So these are the Dirichlet energies.
These are the Dirichlet energies.
And do they concentrate? I mean, if we, that's in time, right?
It's in time.
And in X, like they concentrate, do they?
You mean if I considered locally energies? So I'm only plotting here the gradient of M. So I'm plotting. I'm sorry. The first picture is for. That's the only thing which I can offer here. Gradient M L infinity and the evolution in time trajectory wise.
I was thinking about the density of the Dirichlet,
Okay.
density.
So no, I don't have that here.
Because I mean,
But they do concentrate.
See whether you have a bubbling off or not.
I mean, the energy here, since everything is basically looking downwards in my picture, and there's only the concentration at the origin, this contribution is essentially giving, I think, the one that you want.
Any questions or comments? So if not, thank you again.